Welcome back, everyone, to another deep dive.
It's great to be back.
So for this one, we're taking a look at something I think is going to be pretty interesting. It's chemical reasoning in LLMs unlocks steerable synthesis planning and reaction mechanism elucidation.
Yeah.
So right away, I think we see what's kind of interesting about this, right? LLMs doing chemistry. What does that even mean?
Yeah, it's a really intriguing title, and it kind of gets at this question of, can we automate chemical reasoning? Can we really imbue these models with an understanding of chemistry that parallels what human chemists are able to do?
And it's funny because we've seen so many papers, where people try to get LMs to like directly generate molecules or do these things.
Right.
And I think we all know that has led to some pretty
interesting results.
Interesting results, yeah.
Yeah.
But this is kind of a different take on it, right?
Yeah, it is.
It's not saying, can the LLM do the chemistry? It's saying, can the LLM reason about the chemistry and help the tools that we already have do a better job?
Yeah, exactly. And I think that's a really important distinction because, as you alluded to, LLMs have had some trouble generating valid chemical structures, things like smile strings, which are a way to represent molecules as text.
Yeah.
And so rather than trying to force them to be these perfect molecular architects, this paper says, well, let's use them for what they're good at, which is reasoning, understanding, evaluating, and then let's use that to guide the tools that we already have that are much better at manipulating those structures directly.
Yeah, and if we think about it, I feel like so much of human ingenuity is not necessarily like being the best at every single tiny little task.
Right.
It's about figuring out how to get the right tools to do the job for you.
Absolutely.
And that's what they're doing here. It's like, instead of saying, oh, the LLM has to be able to move the atoms around and make the molecule itself, it's saying, no, the LLM can be like the strategist.
Right.
And it can be the one saying okay, we need to build this ring first, and then we need to protect this functional group, and then we can do this. But it's like the high level strategist.
Right.
And then you have your, worker bees that are actually doing the atom moving, so to speak.
Yeah, I love that analogy. It's like the LLM is the master chemist who has all of this experience and intuition.
Yeah.
And they're guiding these little robotic arms to actually carry out the synthesis.
Yeah, and I think that's a really powerful idea because it gets at this core concept of what AI can do well right now.
Exactly.
It's not necessarily about replacing humans at every single task. It's about augmenting human capabilities and letting us do things that we couldn't do before.
Absolutely. And I think that's where the real excitement lies with this kind of research.
Yeah, so let's dive into the paper a little bit and see how they actually implement this.
Okay, sounds good.
So the introduction, obviously they set the stage by talking about this long-standing goal of automating chemical reasoning. They talk about how important it would be if we could really accelerate drug discovery and material science and all these things.
Right. And they point out that traditional machine learning has had some successes, but it's really struggled with this high-level strategic thinking that you were talking about.
Yeah, it's like it can figure out, okay, if I mix these two things together,
right,
I get this reaction.
Right.
But it can't figure out oh, but that's not actually going to help me 5 steps down the line.
Exactly. And they really emphasize that human chemists are doing this all the time. They're thinking about, okay, if I form this bond now, is that going to cause a problem later on when I try to introduce this other functional group?
Yeah.
They're thinking about what starting materials are readily available and cost effective. And they're thinking about all of this in conjunction with an understanding of how the reactions actually work, the mechanisms.
Yeah, it's not just can I get from point A to point B? It's can I get from point A to point B in a way that is elegant and efficient and doesn't use, super expensive reagents that I can only get from the top of Mount Everest or something.
Right.
So then they go on to talk about LLMs, right? And this is where it gets really interesting because, as we said, they're not trying to get LLMs to actually draw molecules or anything.
Right.
But they're saying, look, LLMs have this amazing ability to understand chemical concepts at different scales.
Yeah.
They can understand what a functional group is. They can understand what a reaction mechanism is. They can even understand high-level strategic concepts, oh, I need to do a ring formation at this point.
Yeah, and it's remarkable how they're able to extract this information from the literature and reason about it in a way that seems almost intuitive.
Yeah, it's almost like they're developing a chemical intuition, even though they've never actually done an experiment in their lives.
Right.
And so then they go on to say, okay, so how do we actually use this for something useful?
Yeah, so they lay out their central thesis, which is to combine this LLM reasoning with these traditional search algorithms that are very good at manipulating chemical structures.
Yeah.
And they focus on two main applications: steerable synthesis planning, which is basically figuring out how to make a molecule, and mechanism elucidation, which is figuring out how a reaction works.
Right. So let's talk about synthesis planning first, because I think this is where like the real power of this approach really shines.
Yeah, it's a really challenging problem. You know, if you think about it, there are so many different ways to make any given molecule, and the number of possible synthetic routes explodes exponentially as the molecule gets more complex.
Yeah, it's like a combinatorial explosion, right?
Right.
And so traditional computational approaches, they've used things like, these heuristics, these rules of thumb, these kind of like educated guesses, to try to navigate this giant space of possibilities.
Yeah. Right. And they've had some success, but they often miss these strategic considerations that a human chemist would naturally take into account.
Yeah, and it's hard to encode that kind of knowledge into a computer program, right?
It's very difficult because it's often tacit knowledge. It's not something that's easily written down as a rule.
Yeah, it's like, oh, I've done this 1,000 times.
Yeah.
And I know that if I do it this way, it's going to be a lot easier than if I do it that way.
Right.
But you can't really explain why, you just know it.
Exactly. And that's where the LLMs come in, because they're able to learn these kinds of patterns and relationships from the data.
Yeah, so what they did was they said, okay, well, let's let chemists actually specify the strategies that they want to use in natural language.
Right.
So you can say something like, I want to build this ring as early as possible in the synthesis, or I want to avoid using, this particular reagent because it's toxic or whatever.
Right. Or I want to try to mimic a biosynthetic pathway, the way nature makes this molecule.
Exactly. And then the LLM can take that natural language input and use it to guide the search algorithm.
Right. So it's like having a conversation with the computer about how you want to approach the synthesis.
Yeah. And this is what I think is so cool about this, because it's making these tools so much more accessible to chemists.
Right.
You don't have to be a computer scientist to use them. You can just talk to them in your own language.
Exactly. And I think that's really important for the adoption of these tools in the real world.
Yeah. So let's talk about the results they got, because they're pretty impressive.
Yeah, they are.
So they found that even like current commercial LLMs, like the ones that are available right now, can actually do a pretty good job of reasoning about synthetic routes.
Yeah, they were able to evaluate individual reactions, and they were able to evaluate overall strategies.
And what's even more interesting is that the performance scales with the size of the model.
Right. So the bigger the model, the better it does.
Which kind of suggests that this chemical reasoning ability is something that emerges as these models get larger and more sophisticated.
Yeah. It's not something that you can just program in. It's something that they're learning from the data.
And they did mention one limitation, which is that when you get to really, really long synthetic sequences, like, 20 steps, 30 steps, the models can sometimes struggle to keep track of everything.
Yeah, it seems like they lose context a little bit.
Yeah, but even then they were still able to pick up on some of the relevant chemical features.
Right.
So it's not like they were completely lost.
Right.
But it's definitely an area for future research.
Yeah.
So one of the coolest things they did was they looked at the historical synthesis of atorvastatin.
Oh, yeah. Lipitor.
Which is like the active ingredient in Lipitor.
Right. One of the best-selling drugs of all time.
And strychnine, which is a really complex natural product.
Yeah. It has a really fascinating structure.
Yeah. It's like one of those classic, like, organic chemistry, like, challenge molecules. And so they gave the LLMs these expert-crafted prompts that described specific strategic elements of these known synthetic routes.
Right.
So they didn't give them the actual routes. They just said, like, okay, we want to build this ring first, and then we want to do this, and then we want to do that.
Right.
And the LLMs were able to identify the correct routes and give them high scores.
Yeah, it was really impressive.
It was able to actually understand what the experts were talking about and connect that to the specific chemical transformations that were needed.
Yeah, and I think that's a really powerful demonstration of the potential of this approach.
So let's move on to the second application, which is mechanism elucidation.
Oh.
So for those of you who aren't chemists, reaction mechanisms basically describe this step-by-step process of how a reaction happens.
Right. It's not just about knowing what goes in and what comes out. It's about understanding how you get from A to B.
Yeah, it's like the difference between knowing that you can drive from New York to LA and actually having a map of the route that you're going to take. And so understanding mechanisms is really important for all sorts of things.
It is.
It's important for explaining why reactions happen the way they do. It's important for predicting new reactions, and it's even important for optimizing reaction conditions.
Right.
But figuring out mechanisms is hard.
It is. It can be very challenging.
And so there are a lot of computational tools out there that try to help with this.
Right.
But they often run into problems.
Yeah, they often lack the chemical intuition to distinguish between plausible and implausible mechanisms.
Right. They might come up with a mechanism that, like, technically works.
Right.
But no chemist would ever actually do that.
Exactly.
And so what these researchers did was they took a different approach.
Yeah, they defined a very basic set of fundamental electron-pushing moves.
Yeah, so like ionization attack, those kinds of things.
Right.
And then they had the LLM evaluate the plausibility of each individual step.
Right. So it's like the LLM is acting as a guide saying, okay, this step makes sense chemically, this step doesn't.
Yeah. And it's not trying to predict the whole mechanism at once. It's just saying, like, okay, is this one step reasonable?
Right.
And then it goes on to the next step and so on.
Exactly.
And they got some pretty good results with this.
Yeah, they did.
The best performing LLMs were almost perfect on the simpler reaction mechanisms.
Right.
And even on the more complex ones, they were still able to do a decent job.
Yeah, and interestingly, they found that giving the LLMs some hints about the expected mechanism really helped.
Yeah, so like if you gave it like a textbook description of the mechanism,
right,
it would do a lot better,
yeah,
especially the less capable LLMs.
Yeah.
So again, this kind of points to the idea that LLMs can benefit from human expertise.
Absolutely.
It's not like they're going to replace chemists anytime soon.
Right.
But they can be really powerful tools if they're used in the right way.
Absolutely.
So the discussion section of the paper is basically where they kind of sum up their main contributions.
Right.
And they highlight this new framework that they've developed for combining LLM reasoning with traditional search algorithms.
Right. And they emphasize the LLM's ability to analyze chemical objects at multiple levels of abstraction.
Yeah, like from atoms to functional groups to reactions to entire synthetic pathways.
Right.
And they also talk about the limitations of the approach. You know, they're very honest about the fact that it's not perfect.
Yeah, they point out that it can struggle with very complex synthetic routes.
Right.
And they suggest that this might be due to biases in the training data.
Yeah, like the LLMs might be biased towards certain types of reactions or certain ways of thinking about chemistry.
Right.
But overall, they're very optimistic about the future of this approach.
Yeah, they see it as a really promising avenue for developing more intuitive and powerful computer-aided chemistry systems.
Yeah. I think it's exciting.
I do too.
So the methods section is pretty technical, but I do want to highlight a couple of things.
Okay.
So they used a variety of different LLMs for their experiments, including some from OpenAI and Anthropic.
Yeah.
And for the synthesis planning experiments, they integrated the LLMs with a software package called a ZynthFinder.
Which is a really powerful tool for exploring chemical synthesis space.
Yeah, it's been around for a while, and it's been used for a lot of different things.
Right.
But this is the first time that it's been combined with LLMs in this way.
Yeah, it's a really innovative approach.
And then they also spent a lot of time creating these benchmark data sets
Right.
to evaluate the performance of their approach.
Yeah, and they were very careful to make sure that the data sets were diverse and representative of real-world chemistry.
Yeah, because if you just test it on like toy problems, then you don't really know how well it's going to work in practice.
Right.
So the supplementary information is actually really interesting. It has a lot of cool stuff in it.
Yeah, it does.
So for example, they showed that LLMs can generate textual descriptions of synthetic routes just based on the starting materials that are used.
Yeah, that was really cool.
Like you give it a list of starting materials and it can say, okay, well, you could use these to make this molecule by doing this and then this and then this.
Right. And those descriptions actually correlated pretty well with the actual similarities between the sets of starting materials.
Yeah, it's like it was able to understand the relationship between the starting materials and the target molecule, even without being given any explicit information about the synthetic route.
Right.
They also found that LLMs can identify functional groups in starting materials.
Yeah.
Which is something that, you know, chemists do all the time.
Yeah.
But it's actually kind of a tricky problem for computers.
It is, because functional groups can be kind of subtle and they can be hidden within a larger molecule.
Yeah. And sometimes they're not even obvious to human chemists.
Right.
But the LLMs were able to do a pretty good job of this.
Yeah, they were even able to identify some functional groups that traditional rule-based systems missed.
Which is really impressive.
It is.
And then perhaps most impressively, they showed that LLMs can actually identify unnecessary or missing protecting groups in proposed synthetic routes.
Yeah, that was really interesting.
So protecting groups are these things that chemists use to temporarily block a functional group from reacting.
Right.
So like if you have a molecule with 2 alcohols on it,
right,
and you only want to react one of them,
right,
you can put a protecting group on the other one so that it doesn't react.
Exactly.
And then later on, you can take the protecting group off.
Right.
And so this is a really important concept in organic synthesis.
It is.
But it's also something that can be really tricky to get right.
Yeah, you have to be very careful about choosing the right protecting group. And you have to make sure that you can remove it later on without damaging the rest of the molecule.
And so the fact that LLMs were able to identify cases where protecting groups were either unnecessary or missing,
right,
really suggests that they're developing a sophisticated understanding of reaction selectivity and potential side reactions.
Yeah, it's like they're starting to think like a chemist.
Yeah, it's really cool.
It is.
So I think it's important to kind of step back for a second and think about the historical context of this work.
Okay.
Because computer-aided synthesis planning has been around for a long time.
It has. It goes back to the 1960s with systems like Dendrol.
Yeah, and those early systems were mostly rule-based.
Right. They relied on experts to encode their knowledge into a set of rules.
Yeah, and that worked okay for some problems.
Yeah.
But it was very limited.
It was.
And so then machine learning came along.
Right.
And people started using machine learning to predict things like molecular properties and reaction outcomes.
Right.
And that was a big step forward.
It was.
But it still didn't really solve the problem of capturing this high-level strategic thinking that human chemists do.
Right.
And so the emergence of LLMs is really a game changer.
It is.
Because it's the first time that we have a tool that can actually learn these kinds of complex patterns and relationships from the data.
Yeah, and I think that's why this paper is so important, because it's showing us that LLMs can be used not just for, generating text or translating languages,
right,
but for actually reasoning about complex scientific problems.
Yeah, and I think it's going to have a huge impact on the field of chemistry.
Yeah, I agree.
So what are some of the real-world implications of this research?
Well, I think the most obvious one is that it could really accelerate the discovery of new drugs and materials.
Right.
Like if we can use computers to efficiently explore vast numbers of potential synthetic routes,
right,
then we can find new drugs and materials much faster.
Yeah, and we can also find drugs and materials that are more effective and have fewer side effects.
Exactly, and it could also lead to a deeper understanding of reaction mechanisms,
right,
which could help us to develop new reactions and optimize existing ones.
Yeah, and it could also make chemistry more accessible to a wider range of people. Yeah, like if you don't have to be an expert in organic synthesis to use these tools, then more people can contribute to the field.
Exactly.
And then I think the most exciting possibility is that it could lead to new forms of human-AI collaboration.
Right.
Where AI is not just a tool, but a partner.
Yeah, it's like having a really smart research assistant.
Yeah, that can help you to brainstorm ideas and evaluate different approaches.
Exactly.
So for our Novel Notions segment, I thought it'd be fun to kind of speculate about some potential future research directions.
Okay, sounds good.
So one idea that I had was, what if we could integrate real-time experimental feedback into the LLM-guided mechanism elucidation process?
Yeah, that's an interesting idea.
So like imagine a system where the LLM proposes a mechanism,
right,
but then it also suggests specific experiments to test that mechanism.
Yeah.
Like it might say, okay, we need to do an isotopic labeling study to see where these atoms end up.
Right.
Or we need to measure the rate of reaction under different conditions. And then the results of those experiments could be fed back into the LLM.
Right.
So that it could refine its understanding of the mechanism.
Yeah, it would be a closed loop system.
Yeah, and this could be really powerful because it would allow the LLM to learn from real world data.
Right.
And it could potentially lead to the discovery of mechanisms that we would never be able to figure out on our own.
Yeah, it's a really cool idea. Another
idea that I had was, what if we could develop what we might call adversarial strategy generation for retrosynthesis?
I'm not sure I follow.
So instead of just asking the LLM to find a synthetic route that works,
right,
what if we asked it to find the most challenging route possible?
Oh, interesting.
Or the least intuitive route.
Yeah.
Like a route that no human chemist would ever think of.
Okay, I see where you're going with this.
And this could be really useful for a couple of reasons.
Yeah.
First of all, it could help us to stress test existing synthetic methods.
Right.
Like if we can find a route that breaks our current methods, then we know that we need to develop better methods.
Exactly.
And second of all, it could lead to the discovery of entirely new synthetic strategies.
Yeah, like if the LLM comes up with a route that's completely different from anything we've ever seen before, then that could be a real breakthrough.
Yeah, so I think there's a lot of potential for future research in this area.
I agree. It's a really exciting field.
So to wrap things up, I think this paper is a really important contribution to the field of computer-aided chemistry.
It is.
It's showing us that LLMs can be used for much more than just generating text.
Right.
They can be used to reason about complex scientific problems, and they can be used to guide traditional algorithms in new and innovative ways.
Yeah, and I think it's just the beginning.
Yeah, I agree. I think we're going to see a lot more research in this area in the coming years.
I'm sure we will.
And I think it's going to have a huge impact on the way that chemistry is done.
I think so too.
So for those of you who are interested in learning more about this paper, there's a link in the episode description.
And as always, we encourage you to share your thoughts and ideas with us.
Yeah, we'd love to hear what you think.
Absolutely.
So until next time, happy reasoning. Take care.
Bye.